Hi there, my name is Christopher Worst and welcome to the final video for Homework 6 for MEB, the final video for MEB. This one's asking us to derive the lever rule and use it to explain how the ratio of the vapor-liquid fractions change in a closed container of binary mixture at a fixed temperature as the pressure is increased and the contents transition from all vapor to all liquid. Seems simple enough? Well, as you can see behind me,
There we go. We have a pressure graph where pressure is on this side, the components x1, z1, and y1. We've already explained them, the mole fraction of liquid. I'll write liquid, vapor. Would you like to write, pen? Thank you. Vapor, that's better. Over here, and then of course Z1 is somewhere in the middle. It's that weird state of there's some vapor here, there's some liquid here, we don't know how much. Now, this lever rule is asking us what happens as this pressure goes from effectively here, so that Z1 is equal to Y1, goes up and up and up and up and up to about here, where Z1 is equal to X1, where it's all vapor until it's all liquid. And I'll draw a little arrow. Okay. So, in order to do that, we want to make a little few observations here for use later. So we notice that there are two distances here concerning Z1. There is the distance from Y1 to Z1, and of course we're going to read this graph left to right, which means that y1, this distance is equal to y1 minus z1, and this distance here, this distance here is z1 minus x1. So, if we go back to some of the ideas that we talked about in some of the earlier parts, such as the total mole amount is equal to the moles in the liquid phase plus the moles in the vapor phase, as well as combining the Z1, Y1, and X1 into this, so that we have F times Zi equals L times Xi plus V times Yi, which is of course the total moles of component I is equal to the total moles of component I in the liquid phase is equal plus the total moles of component I in the vapor phase. We have all of that. We've already done that. Now, what we want here, we have these two relationships here, the distance between the vapor and Z1, the liquid and Z1, and X1 and Y1, and all of that. Now, we only want L and V and X1 and Y1 and Z1 because we know those. We don't know F. So we're going to just substitute this in. So, L plus V multiplied by Zi is equal to L times Xi plus V times Yi. That means that liquid plus vapor multiplied by Zi, the total moles of component I, is still equal to the total moles in the liquid phase of component I plus the total moles in the vapor phase of component I. Now, if we factor that out, come on pen, plus V Zi is equal to L Xi plus V Yi. Something interesting happens when you subtract these two over. You get L Zi minus L Xi is equal to V Yi minus V Zi. Now, so what? Who cares? Well, once you factor those two out, you get some interesting distances. You get your distances between the 2 points. So, if we factor them out, we get L times Zi minus Xi is equal to V times Yi minus Zi, Zi minus Xi, Yi minus Zi. Okay, so what happens? So now we're just going to divide the two, and then I'll explain why it matters. So finally, it goes V over L is equal to Zi minus Xi divided by Yi minus Zi. So who cares? We did all that, what does it matter? Well, if you'll notice, this is the relationship, the ratio to amount of vapor to amount of liquid. If you go up in pressure, you notice that the distance between Z1 and X1 becomes smaller. This becomes smaller. And you know that the distance between Yi and Zi becomes larger. So that means that we are having more liquid coming. So as the amount of liquid grows, so does the distance between Yi and Zi. And then conversely, if you flip it downwards, it means that the distance between Yi and Zi, of course, the amount of liquid there, the difference between the amount of liquid moles there are and the total moles there are, decreases, and it increases for the amount of vapor and total effectively converge, and then the amount of the difference between the total moles and the amount of vapor moles grows larger. That means, as long as the total moles are staying the same, that as you go down, we know that the amount of moles in liquid grows smaller and smaller. And as you go up, the amount of vapor goes bigger and bigger, and vice versa. So with that, if you wanted to do that calculation, you could figure out at any given amount of pressure, or as as pressure changes, you could figure out exactly how much liquid or volume you have, or what that ratio is. So with that, we've done what the homework is asked, and I hope you have a wonderful day.